Welcome to another video explaining the universe using the particle model. Today's video is about the Pioneer anomaly, one of the anomalies for which there seems to be no explanation. But first, a message about the book Dave and I have written. Yes, the name of the book is Principia Mathematica II, and it's available on Amazon. You can buy it in paperback, full color, expensive, costs $35, or you can get the ebook. You can buy it for $3. A simple link to the book is this link, tpm.thehilster.com. So on to the Pioneer anomaly. That's today's video. These are the previous videos I've had about charge, about equations. I did one recently on the transformer. Still working on the RO load. There's a part of the equation, the physics that I'm missing that is causing it not to work yet. So part of more work to do. I'm not sure when I'm going to get that done. So the Pioneer 10 and 11, the Slowdown is the anomaly. Pioneer 10 and 11 were launched in 1972 to explore Jupiter and Saturn. These remarkably successful and durable spacecraft fulfilled the expectations of their designers. The last bits of data from the Pioneer 10 were received in early 2003, following over 30 years of continuous operation. The spacecraft was 12 billion kilometers from the sun, shot from the Earth, moving away from the Earth and out towards Jupiter and Saturn. This is a picture of what it would have looked like. They would have looked like. However, once they passed beyond the orbit of Uranus, the radio signals sent back by the aging craft have been shifted progressively shorter wavelengths. This implies that they are decelerating slightly, and no one knows why this is happening. Possible causes. A number of possible causes have been ruled out by Philip Lang and Anthony Liu, working under a NASA Office of Space Science grant. This is the list. Errors in the software. The gravity of the Kuiper belt and gravity from the galaxy. Errors in the planetary ephemeris, that's where the planets are in their effect. Errors in the values of the Earth's orientation, precession, and nutation. Non-gravitational effects from the solar pressure and attitude control maneuvers. Wow. Solar wind and interplanetary mediums. Nominal thermal radiation and plutonium half-life. Drifting clocks, general relativity, and the speed of gravity, hardware problems, and the tracking stations. All of these ideas were considered, and none of them explained the slowdown. However, no explanation based on conventional physics. That's all of that has been found. The effect is so persistent that it could indicate some physical principle not yet considered in previous explanations of the motions of the planet. Meanwhile, Pioneer 10 is on its way to the giant star Aldebaran, estimated time of arrival 2 million years from now. It's going to take 2 million years. Here's a picture that was taken on Sunday, July 15, 2012. where the planets Venus and Jupiter join with the red giant star Aldebaran and the waning crescent moon in a quadruple conjunction. That is, they all came together in that morning. Venus, Jupiter, our moon, and Aldebaran all located together at 65 light years away. That's how far away it is. The star is practically a neighbor to the Earth. Its apparent magnitude is about 0.85, making it the 14th brightest star in the night sky. 65 light years away. How far away is 65 light years? Well, you can convert that to astronomical unit. 65 light years is 4.1 million astronomical units. One astronomical unit is the distance between our planet, Earth, and the Sun. That's 93 million miles wide. Now, here's a picture of our galaxy, which in this drawing is shown as 100,000 light years across the full diameter. It's the width of the disk. This tiny line that's shown here is 1,000 light years. Our sun is 28,000 light years from the center of the galaxy. So we're located right here. Now, 65 light years away from here, this is 1,000. Just this small distance is 1,000. So somewhere left, right, in, out, top, bottom is Aldebaran. And so, yeah, when they say it's our neighbor at this scale, we're practically on top of each other. Okay, so let's get to some of the explanation of the slowdown. But first I'm going to talk about light being slowed down. I've done a previous video titled Redshift and Tired Light, and I will put this in the information of this video when it's released, so you have easy access to the link and you can watch my explanation of redshift and tired light. From Wikipedia, in physics, redshift is a phenomenon where electromagnetic radiation, such as light, from an object undergoes an increase in wavelength. And the primary mechanism that they talk about causing that increase is the fact that the star, that distant star, is moving away, and as it moves away, it causes a redshift. This is how they explain the fact that the universe is expanding. Since the speed of light is constant, the redshift means the star is moving away. Okay, redshift and the expanding. It is assumed that the distant star emits light with the same spectral pattern as a nearby star. And I'm going to go into that in the next slide. It's assumed that the speed of light is constant, does not change. If the star is not moving, it should give the same spectral pattern as a near star, whether it's close or far, if it's not moving. So there would be no redshift or blue shift. Speaking of blue shift, at the Andromeda galaxy, which is our closest galaxy galaxy in I'm having trouble here. All the stars in the Andromeda galaxy are blue shifted, not red shifted. Why? Because Andromeda galaxy is moving closer. If the star is moving away, the wavelength will increase, hence the frequency shift towards red, and therefore they conclude that the universe is expanding. Now here's the spectrum for a near star. It's called the absorption spectrum because most of the light is emitted, but there are spots where the light is not emitted, and these are the spots that you don't see. However, as in the lab, if you burn hydrogen, you don't get all the rest of the light, but you get the lines in the same spot. So this is why we know many of the stars are burning hydrogen. But a distant star that's moving away, the wavelength gets longer. The speed of the light is constant, and when you get for a distant star, you get these bars. They're actually not here; they're over here somewhere. It's called redshift, and they're comparing it to the hydrogen spectrum. But particle model has what's called the G2 particle field, and that causes what is drag, and this is what they don't have for an explanation. The G2 particle field is the sustaining force of the G1 particle stream. That's light. This is the G1 particle stream, light that has peaks and valleys and hence a wave. The G2 particles are hitting the G1 from all directions. It's at left, right, top, bottom, and front and back. Drag is caused by the fact that the head-on collisions are stronger while the rear-end collisions are weaker. This causes a G2 gravitational slowdown. G2, gravity particle field, causes a slowdown. Now, what happens here is interesting, and this is how it explains the redshift. So assume that this finger is an observer, and I got two peaks coming by the observer. If it's come by very fast, the time between the two peaks is very short. But if the light, G1 light, slows down, the time between the peaks is longer. And so what we detect with our eyes and with the equipment is the time between peaks. So a slowdown would make it look like the wavelength was longer, when in fact, the wavelength stays the same. Because all of the particles in the stream slow down. These slow down, these slow down. Wavelength doesn't change. But when it slows down, the time between peaks get bigger, and that makes it look like a redshift. So the G1 particle field causing drag on a stream of light coming from a distant star will have a redshift even when the star is not moving. Now it gets more complicated because things do move. So, and I want to repeat this last paragraph. However, once the spacecraft, the radio signals sent back by the aging craft have been shifted to progressively shorter wavelengths. Now we're talking about shorter wavelengths. The spacecraft, just like, is moving away, and it causes a redshift. As it's moving away, it goes further and further. It's not going faster, it's just moving further away. It causes a redshift. But after it passed Uranus, which means it was almost out of our solar system, the radio signals shifted progressively shorter wavelengths. This implies that they are decelerating slightly and no one knows what's happening. Now here's an interesting chart I got from this link, and it's all the radio frequencies. And you got high frequency down to low frequency. Very low frequency and low frequency is for maritime and radio navigation, that all our ships and crafts out there use that. Here's AM radio and more aviation. This is for airplanes. Here's shortwave radio, CB is allocated here. Television, FM radio in very high frequency. Ultra high frequency is television, mobile, phones, GPS, Wi-Fi, and 4G networks. Satellite communications and radio astronomy is up here. So somewhere up here is where the spacecraft is probably sending the signal. So I'm going to assume it's here. And the fact that the spaceship is moving away, causing a redshift, means that when they adjust their radio detector, here it is. When they adjust their receiver to receive the signal from the spacecraft, they have to move it to the left. They have to move it from here, maybe all the way back to here. But when it gets past Uranus, now it's still redshifted, but it's less and less and less. It's a blue shift in that case. So that's what's happening. They have to adjust their receiver to find the frequency. They know what frequency is being sent, and they have to adjust off frequency, either starting with the red shift first and then slightly getting this blue shift as it passes Uranus. The G1 particle field causes drag. Now, I just mentioned G2 causes drag on light. G1 causes drag on the spaceship. G1 particles are hitting the spacecraft from all directions. Drag is caused by the fact that the head-on collisions are stronger while the rear-end collisions are weaker, causing a G1 gravitational slowdown. So as the spacecraft moves this way, it has head-on collisions with the G1 particle field that's going to slow it down. Pioneer 10 and 11 spacecraft are slowed down by this particle field, and this is the force that they had not considered, because this force only exists in the particle model. Pioneer slowdown. Science suspects that there is an unknown force that causes the spacecraft to slow down. TPM suggested that the unknown force is the G1 particle field that causes it. Here's a note. Level 1 objects never get close to the speed of light, because at that point, the G1 drag is infinite. All the objects, all these large objects are Earth, the suns, the stars, the planets, the asteroids, all these objects, they don't move very fast. If there was a force that somehow got behind them and pushed them to move them faster, the drag would get stronger. They never get close to the speed of light, then you can understand why. People, when they observe these objects, these larger objects, why they say nothing goes faster than the speed of light. It's the drag that keeps us from doing that. And unfortunately, yes, the spacecraft won't go to the speed of light. Our bodies in the spacecraft won't go faster than the speed of light because of this G1 gravity slowdown. And is there an expanding universe? Well, there are two factors to consider at least, besides the list of all the things that they had on that one list. Stars moving away from the Earth and Earth moving backwards. Both of those would cause a redshift. G2 gravity causes a slowdown of G1 light, causing the redshift of light. When you start applying the particle model, you got to apply all these things, not only what they considered before, but these two factors. How much of our measured values is caused by the motion and how much by drag? I don't have the data to answer that question. Based on G2 drag, it is my opinion that the universe is not expanding. It is static, but dynamic or moving. It's always moving, but it's not expanding. Final note, G2 speed could be as high as c squared. That's probably its upper limit. It's probably much less than that. G1 light can move faster than c, the known value of the speed of light, because G2 drag is not large at that point. And therefore, if there was a force that caused it to accelerate, light could go faster than c. But if it ever tried to get up to this G2 speed, it would have severe G2 drag. Sorry, my name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. You can do that by sending me an email at particleguru@gmail.com, or comment, hit the comment button in the video. Thank you for your attention.